10.4, polar coordinates and polar graphs. Well, this page should look a little bit familiar as we did this in the introduction, video 1. We did this entire page. So you should be able to go from those notes and write this material down. However, if you want to just do it from this video, pause the video and go ahead and write these notes down. So in our textbook, there are special polar graphs on page 735. They are also included in this section of notes a couple of pages back on page 143. Okay, you should know these graphs. You should recognize that when you have an equation of this form, a plus or minus b cosine theta, it will reflect across the x-axis and there will be an inner loop because a over b will be less than 1. When a over b equals 1, you will have a dimple, really actually more of a puncture, right? When a over b is between 1 and 2, you have what's called a dimpled limicon. And when a over b is greater than 2 or equal to it, you have a convex limicon. Now, what makes a region convex? You can take any 2 points anywhere in the region and connect them, and the segment connecting them stays inside. If that is not true, then you do not have a convex. For instance, here, I could put a point here, and connect them, and the segment would not stay inside the region. Certainly, you can see that's true here. But a convex limicon is one where it looks a lot like a dimpled, but it's a little less flat. Now, what happens if our equation is a plus b sine theta? It's going to look like all of these, except for it will go reflect across the pi over 2 radial arm, or what you know as the y-axis. Now, these are rose curves. A nice thing to know about rose curves is if n is odd, you have an odd number of petals. If n is even, you have 2 times n number of petals. So here is n is 3, and we saw that it repeated over itself, so it traced it twice. Here, n is 4, so 4 theta is going to give me 8 petals. Notice that a cosine 4 theta in this problem is going to reflect across the x-axis, but do you know that what would happen if it was a sine 4 theta? I would suggest graph that and see what you find out. Here is a sine n theta where n is odd. We're going to have n petals. If n is odd, notice that for sine, it will reflect across the pi over 2 radial arm. In this problem, in this one, again, they do interesting things because of the angles. And then these are circles and lemniscots. Well, to find the slope of a tangent line to a polar graph is f of theta. We can use x equals r cosine theta and y equals r sine theta and the product rule. So let's think about this. dy dx is going to be dy d theta over dx d theta. Well, let's look at dy d theta, the derivative of y with respect to theta. Okay? R times the derivative of sine plus sine times the derivative of r. dx d theta. R times the derivative of cosine plus cosine times the derivative of r. And again, dx d theta cannot be 0. Now, you don't have to memorize this formula because you can always derive it. All right, nothing cancels, but you can always derive it as long as you know x equals r cosine theta and y equals r sine theta. Now I'm going to show you a little more specifically that work. Here is y equals r sine theta, dy d theta, r times the derivative of sine plus sine times the derivative of r. Here is x is r cosine theta, dx d theta, r times the derivative of cosine plus cosine times the derivative of r. This goes on top, this goes on bottom. There you go. Let us recall from section 10.3, we had dy dx equals dy dt over dx dt. So dy dx equals dy d theta over dx d theta. And let's let x equals r cosine theta, and r is going to be a function of theta. So this would be f of theta cosine theta, and y equals r sine theta would be y equals f of theta times sine theta. Again, following product rule with my proper notation, substituting in. So what we learned in 10.3 with my derivative in parametric form, this is just another way to think about parameters. My theta is my parameter now instead of t. Find dy dx and the slope of the graph of the polar curve at the given value of theta. Here is my r. Here is my theta equals pi over 2. Let us remember, y is r sine theta, x is r cosine theta, and my r prime is going to be 2 times the derivative of sine, which is cosine theta. Here we go. Okay, our numerator is going to be dy d theta. Here is y as a function of theta. The derivative is r times the derivative of sine plus sine times the derivative of r. Denominator is dx d theta. R times the derivative of cosine, which is negative sine, plus cosine times the derivative of r prime. Now I do have to say, this isn't going to simplify any better. You can't do a lot with it. What we can do here is we can recognize that I can distribute the cosine. So we get 2 cosine theta plus 2 sine theta cosine theta plus 2 sine theta cosine theta. So I got 4 of those. Here I have negative 2 sine theta times the negative, and negative 2 sine squared theta plus cosine squared theta. I can simplify and put in some double angle formulas and whatnot, but I don't need to. Just go ahead and substitute your pi over 2. Now, let me say this about AP exams and just in general. You always need to show dy dx. You need to show that step. And it's absolutely not a bad idea to say this is dy d theta over dx d theta. That is not a bad idea. And now we're going to evaluate at pi over 2. You can show the step where you're substituting pi over 2, or you can just go for the values, but we get 0. So dy dx at pi over 2 is 0. There you go. So I have a horizontal tangent line. Okay, pause your video and write down the work for this problem. Number 6. Again, let me remind you, let me explain the problem before you try to write it all down. Find all points, the points of horizontal and vertical tangency to this graph. Oof. So let us remember, x is r cosine theta, y is r sine theta. So dy dx is dy d theta over dx d theta. Here's our general form for that, r cosine theta plus r prime sine theta on top, negative r sine theta on bottom plus r prime cosine theta. Now we can do our work to get this. So here is dy dx, simplifying it out. By the way, let's remember sine of 2 theta is 2 sine theta cosine theta, and sine squared of theta is 1 minus cosine squared theta. That could be useful somewhere. Okay, horizontal means the derivative is 0. So that's where the numerator is 0 and denominator is not. So setting the numerator equal to 0 and doing the necessary work, let's get one function, use a Pythagorean substitution. Do aloha, more aloha, more aloha. Now, notice that what we have here is 2u squared minus u minus 1, which factors to 2u plus 1 times u minus 1 equals 0. So we get 2 cosine theta plus 1 to equal 0, and cosine theta minus 1 to equal 0. And we have to solve for both of those. Cosine of theta is negative 1/2 in quadrants 2 and 3, and here are the angles. Cosine of theta is 1 when theta is 0 or 2 pi, but we want to take 0. Okay, now let's find our r. My r at 0 is 2 minus 2 cosine theta, which is cosine 0 is 1, 2 minus 2 is 0. So at 0, my radius is 0. Now let's look at 2 pi over 3 and 4 pi over 3. That's 2 minus 2 cosine of 2 pi over 3, which is 2 minus 2 times negative 1/2, which is 3. And also at 4 pi over 3, my cosine value is negative. So my radius is 3. So that is an interesting piece of information. Now for a vertical tangent. Now for a vertical tangent, that's going to happen where our denominator is 0. Set the denominator equal to 0, do the necessary algebra and trig. It didn't really help us to substitute in a double angle identity. You know, I could factor out a 2, and I could make this 2 sine of 2 theta. Doesn't really help us. We still have issues. It was better to leave it like that. But now we need to look at our r. So our r is going to be 2 minus 2 cosine theta. So I need those radii. Let's make a list of all of our theta values where we get what we need. Now we've got quite a few thetas to choose from, but we have to eliminate anything in common. Because at 0, for instance, my dx d theta is 0, and at 0, my dy d theta is 0, and we know we cannot have 0 over 0. So anything in common goes. So that means we have to take out the points that had things in common. Again, we have found our radius. Remember, our points are r theta. So you have to find the r, because the question was, find the points. Once we have our angle, we can find our radius. Once we have our angles, we can find our radius. We throw out the one that is common. There is quite a bit to write down. This is the first part. Pause the video so you can write down all this work. Here is the rest of the page. Pause the video so you can write down all of this work. Your TPs for this section are 23 through 26. Do not use your calculator. And then 35 and 43. See you next time.